Okay, hi. So let's finish up this last bit of Unit 4 business. We are going to talk about expected value today, which is just a real particular kind of problem that you can do that puts all this together, the probability, the counting, and kind of outcomes. So let's get started. So expected value is basically a computation that you do that gives you an average gain or loss of an event that occurs over many repetitions. Okay, so we're not talking about doing something three times, we're talking about many, many repetitions, and then you can make a prediction on what you would expect your outcome to be. And that's what expected value is. And so we compute the expected value by multiplying each of the outcomes by the probability of that outcome and then adding up the products. And I have five quick examples for you today. So here's the steps. And of course, you don't have to use a pretty table like I have here. You could most certainly do something like this and write outcome and probability here. I just made it pretty with a table, okay? Also, so first you identify the outcomes and organize it with a table. Then you compute the probabilities of each of the outcomes listed, and then you calculate that calculate that expected value by saying outcome one times the probability of that outcome happening plus outcome two times the probability of that outcome happening plus so on and so forth. And after you compute all that up, that final answer gives you what you would call your expected value. Okay. And we'll also be interpreting the expected value. And the interpretation of expected value is the expected value tells us what we'd expect on average per trial if the situation happened many, many times. Okay. And I'll kind of give you some wording that you can use and kind of plug and play every time for your answer. You'll kind of see that pattern. So let's look at the first one here. So our first example says you play a game that has 38 outcomes and it costs $1 to play the game. And if you choose the matching outcome with the house, you win $35. What we want to do is find and interpret the expected value. So let me write that here because I didn't write that there here. So we want to find and interpret the expected value. Okay, so first things first, we identify the outcome. Well, we have 38 outcomes, but what are the outcomes? Let's see. First, it costs $1 to play. And then if you choose the matching outcome, you win 35. So we have two outcomes here. We could win, and there we would win $35. Or we could lose. And if we lose, it costs $1. All right. So what is the probability of the outcome? Well, let's just make a supposition. Say that we have cards, right? And there's 38, or no, let's say we have 38 numbers on rocks. Okay. And they're all in a bag. What is the probability that you will pick the same one that say the house picked? Well, there's only one outcome that's going to match those 38 outcomes. So to win, it is one outcome that matches the number that was determined by the house. Okay. And then to lose, well, what's your chance of losing? Well, there's 38 total. It could be 1 minus your chance of winning, or we could say 37 out of 38 because there's only one winner, right? And now when we put it all together here, the expected value is equal to the outcome. So $35 times the probability of getting $35 plus the outcome, -$1 times the probability of getting that outcome, 37 over 38. Now, when you put all this in your calculator and you run it, you get -0.0503. That's the answer. Okay. And so what is our interpretation? The interpretation here is over time, you would expect to lose an average of 5 cents each time you played. Now, to be noted, expected value doesn't give you a probability. Notice that. Expected value does not give you a probability. Expected value gives you an idea on what you may gain or lose if you participate in the game. Okay? So, somebody might consider thinking that, oh, well, I only lose about 5 cents every time. It's worth me losing 5 cents to maybe gain $35 in the whole long run. Anyway, that's some logic. That's some logic that could be done. Okay, let's take a look at the next example. And this kind of goes back to our last lecture. We did a lot with that counting and probability. Remember, it is important to consider that order does not matter when you're drawing the balls for a lottery. That's not really an issue. And so because order does not matter, the 6 numbers you choose matter, but the order of which those numbers come out, again, remember that's what I said last time, the order in which those numbers come out does not matter. So that means that we're going to use that formula for our counting, okay? Now, let's get back here and figure out what our outcomes are. A certain state's lottery, I don't know why this dumb thing unhid. I want it to stay hidden. Thank you. Okay. So it says that a certain state lottery pays out $1 million if 6 of their numbers match the 6 numbers drawn by the lottery commission. The payout is $1,000 if the player matches 5 of the numbers. The balls are numbered between 1 and 48. Find the expected value. Okay, so there's three situations here. First off, you win $1 million. Okay, and you win $1 million, but it costs you $1 to play. So this would be a total of $999,999. That would be one of the outcomes that you got $1 million minus $1. Okay. Another one of the outcomes would be that you win $1,000 minus $1. And so that's going to be $999. And then the other outcome is that you didn't win Jack, right? And you just lost. You're not a winner. And so you're just down $1. Okay. So these are our values of our outcome. Now let's work on our probabilities. Now we just did this in our last lecture. Okay. So let's talk about it for a second. So to win 1 million, remember, let's do the 1 million first. Remember, what do we have to know? We have to know the total, and that is going to be 48, choose 6. And we have to know the event. And the event is of the 6 numbers chose, you got the 6 right. So of the 6 numbers, you got all 6 right. That's what that means. Okay. So that's for the 1 million. Let's go ahead and do for the 1,000. Again, the total is going to be the same because we're still playing the same game, the same lotto game. And then here, the event is going to be of the 6 numbers, you chose 5. Okay. All right. So that's going to be what we're going to put together for this. And then what is the probability that you're not a winner? It's going to be 1 minus the probability that you didn't win at least 1,000, right? Okay, so let's see how this is going to go. So the probability of this guy is going to be 6C6 over 48C6. And then this one is going to be 6. Oh, I didn't finish that event. Hold on a minute. I knew when I started writing it down, I was gonna. So that's what this piece is for sure. And then that's going to be times the other one, which is going to be 42, choose 1. This is the one wrong number. Gotta account for both of those pieces there. So let's do that one. So that one is going to be 6, choose 5 times our 42, choose 1. And all that is over 48, choose 6. Now, there's a couple of things I want to point out and remind you. You can kind of double check this. This might seem like this is crazy, but check it out. 6 plus 42 is 48, and 5 plus 1 is 6. These numbers have to add up for this to be a solid situation. So it's a good double check for you to make sure that you've got that going on there with this complex one. It's not a simple one like on top. This one is more complex. It's multiple events. This was only one event. You get all 6 of them. Yay. This was, you only get 5 of them and you get one wrong. That's a 2 event situation. So that's kind of the difference there. And then finally, the wah wah you lost would be 1 minus you won 1,000. So the minimal. I need to make these bigger. This little table is just tiny. Okay. And so we can put this all together in an equation. Now, I suggest you just like roll it all together like this. Expected value is equal to 999,999 times this crap. I mean, it's better than trying to write all those numbers, especially since you know all this is going to be in scientific notation, which is a absolute nightmare to just try to mess around with. Plus our 999 times this. Minus 1, because that's a minus 1 there. So I'm just going to say minus 1 times this. And after you do the math there, we're going to get negative 0.898. Oops, what happened there? I have no idea. I must have pressed a button on my stylus. Negative 0.898, which means over time, you lose on average 90 cents each play. So as our first example here seemed like, ow, you're losing us 5 cents each time out of $1 to play. Now we're losing 90 cents out of the $1 that we play. So that's not quite as good of a return is what we would say. So we use this for things other than betting and stuff. Let's see how this is used like regularly in industry and stuff like that. Okay. And this is true. This is actually something that they do. Actuaries are actually the name of the people that work in Usually the insurance industry, but it is true that they work in other industries as well. But traditionally, it's been in the insurance industry, and they're paid very, very well for their math abilities. And they sit and they figure out stuff way more complicated than this, but this will give you an idea of where this could actually fit in and work for businesses or whatever. Okay. A 40-year-old man in the U.S. has a 0.242% chance of dying during the next year. An insurance company charges $275 for a life insurance policy that pays a $100,000 death benefit. What is the expected value for the person buying the insurance? Okay, so let's look at what our outcomes are. Well, just to be very frank, we have two outcomes here, right? Somebody dies, or they live. Okay, now, if the person dies with this policy, then they have 100,000 minus the policy that you paid for, which is 275. Oops. So that gives a total outcome of $99,725. And then the other option is you live, and if you live, well, you're just down that $275 premium you pay every year or whatever, okay? Now let's figure out the probability. Now, you know, probability is not a percentage, but we can convert. So we have 0.242% chance means that is equal to 0 point, moving the decimal place 2 places, 0.00242 for the probability of death. Okay, so that is what this probability needs to be. Wasn't it nice? You didn't have to really compute it. Okay, well, what is the probability that you live? It is the complement of dying, right? So this is going to be 1 minus the 0.00242. And I don't know if I didn't even figure out what that number was. So let's put it all together here. So our expected value on our investment of our buying insurance, that's really this, the expected value of the investment of buying the life insurance. You don't have to put all that in your explanation, but it wouldn't hurt. I'd love it if it was in your sentence, but I want to make sure you understand what is it that we're even crunching this number to get. Okay, is this, and we've have the outcome, which is 99,725 times 0.00242 minus the 275, because it's a negative right there. That one's a positive. Times 1 minus 0.00242. When you crank that in your calculator, we get a straight, beautiful negative 33. So our outcome here, we would say over time, Are you seeing the pattern? Over time, here I'll say the customer, I can't even spell T. The customer would expect to lose about $33. Okay. Let's have this one be a you do. Okay. Now this is basic probability. We have 3 outcomes. Outcome 1, outcome 2, outcome 3. So I'm going to you do this for you, and we'll take about 3 minutes. Excuse me. Okay, so let's see what we got. All right, so what are our outcomes here? Well, we get gold, we get silver, we get black. When we get black, we lose $1. When it's silver, our outcome is gaining $2. And if it's gold, you win $4. Okay, now let's set up our probability. So we have to go back to like the first part of unit 1. First off, we have 1, 11, 31. There's 31 total marbles. So what is the probability of getting a gold? There's only one. So 1 over 31. Silver, 10 over 31. And black, 20 over 31. So let's put it together. Pretty straightforward once you see how it sets up. So our expected value of playing this game is going to be 4 times 1 over 31 plus 2 times 10 over 31 minus 1 times 20 over 31. And when we run that math there, we get 0.129. So since we're talking about money here, we're going to say over time, you would expect to gain about, I'm going to have to say about because about 13 cents on average for each game played. All right, good deal. Okay, I hope you did well with that. All right, this is our last one. I wish I could quit saying all right. I'm sorry. I think I keep on saying all right a whole lot. Let's move on. So, a company estimates that 0.4% of their products will fail after the original warranty period, but within 2 years of the purchase, with a replacement cost of $350. If they offer a 2-year extended warranty for $43, what's the company's expected value of each warranty sold? Okay, so what are our two outcomes? Well, first we've got the product fails. And product does not fail. Oh, hold on a second.